Okay,
Yeah.
great. Yeah, so my name is Wynn, Jacobson Galan. I'm a graduate student at UC Berkeley, formerly at Northwestern. And I work with Professor Raffaele Margutti on transients, explosions, and all types of stuff. And today I'm going to be talking about pre and post explosion imaging of a very interesting supernova 2020 TLF that enable us to see what a massive star, a red supergiant star, was doing in the final months before it exploded, and then afterwards in all its complex history and all of its amazing enigma behavior, specifically seeing the star explode prior to the supernova itself. All right, so before I begin, I'd like to make a land acknowledgement. A good amount of this research was done while I was associated with Northwestern. That's located on the land of a number of tribes, nations, and communities whose sacrifices enabled me to be part of that university. I would also like to say that just Keck observations and my affiliation with using Keck for this project was enabled by the sacrifices of Indigenous Hawaiians, and I just like to recognize that before I begin. Okay, so let's start it off. So today I'm talking about the supernova with the barcode 2020 TLF. This was discovered last fall, about a year ago today almost. And here it is in its host galaxy at approximately 37 megaparsecs. It was reported on the 16th of September by Atlas. And then thanks to Keck and thanks to our time on Keck with the Young Supernova experiment, we were able to obtain this classification spectrum, so shown here. It was initially classified by us as a type 2N supernova, so it was probably from the collapse of a massive star, so type 2, and then had all these kind of strange narrow features in its spectra, which are characteristic of, quote, flash spectroscopy or photoionization of a nearby circumstellar material that is ionized upon shock breakout. But then, unfortunately, after that, the supernova became sun constrained, but we were able to continue follow-up photometrically thanks to Swift up until it was became visible to Earth again in ground-based telescopes. So shown here is our complete photometric sequence, our complete light curve. Swift filled in the gaps between our initial discovery and then a lot more of its photometric sequence at later times after, say, 80 days after explosions or so. So as you can see, for people who are familiar with supernova light curves, a type 2 supernova, a type 2P specifically, rises and then has this kind of plateau phase. Some are more linear, declining, or more flat. That's just the result of the hydrogen envelope trying to recombine. Once it recombines, it falls off into this radioactive decay tail. So this is a really beautiful, like, high cadence sequence that we have here, thanks to a number of telescopes around the world. And what I just want to point out here before I move on is that the data discovered prior to the Atlas detection was actually not recovered until we went back and understood what was observed with the supernova prior to the discovery. So it was discovered, we took this flash spectrum. It was really cool. We're going to follow it up later on. But actually, Young Supernova experiment, which is this transit survey that I'm a part of that works with the PS1 telescopes, was actually observing this field for quite some time. So that's kind of a teaser to a later point in this talk that I'll get to about observing the supernova even earlier than it was previously thought it was. So spectroscopically, I'll just highlight the great role of LRES in this. So we have this really great early time spectra. There was, decently high resolution. We could see these narrow emission lines that spectroscopists love because this is like flash spectroscopy. This is a burgeoning field of observing young supernova that are ionizing nearby circumstellar material. And then we were able to follow it up at later times once it became sun constrained. And we see that it evolved actually beyond these narrow features. So not really a 2N, but actually into more like a type 2, more like a type 2P, which has this, broad P Cygni H alpha features and other features that are most commonly associated with just the collapse of a normal red supergiant star of varying sizes. And then at nebula times, we were able to use DEIMOS and the powerful, collecting light of Keck to observe this at much later times. And for those who are familiar with what nebula lines can tell you, the forbidden oxygen line is actually a great tracer of the zero-age main sequence mass of the progenitor. So that was super instrumental in constraining what the progenitor size was. So I'll get back to that when we're talking about the modeling. A couple more highlights of the spectroscopy. So for those familiar with the prototypical like narrow feature or 2N-like feature object, so 1998S is shown in red here compared to 20 TLF at a similar phase relative to peak. And it's pretty much nearly identical. So this is really like a twin object in that way. And so what these narrow emission lines are, to recap, is the shock breaks off from the supernova from the stellar surface. It ionizes this nearby circumstellar material if it's there. If it's there, then what happens is the shock will propagate throughout the CSM. It will continue to photoionize and keep these lines illuminated until the shock passes through the shell of circumstellar material. And it's super fascinating to find these lines and to see these lines in the spectra, because what we're doing is we're tracing and mapping the progenitor mass loss history in the final weeks, the final months, right before the star exploded. So this is like a really burgeoning field of rapid early time spectroscopy, as I showed here on the right. This has been done for other objects. Keck has been instrumental in doing this for past objects and will be instrumental for other objects in the future. Because it's a really powerful telescope. It can get flash spectroscopy of a wide variety of events, not just nearby ones. So that's really, really great. Moving on to the novel part of this talk. So we know that this star was losing mass. It clearly had some sort of circumstellar material around it at the time of explosion, which was then ionized by this propagating shock front. What I said was actually earlier on was that the Young supernova experiment was actually observing this field for hundreds of days before explosion. And what we wanted to do was we wanted to look back in archival imaging of this survey, because this was a nearby object. It clearly had some interesting outbursts, properties to it, and see, hey, did this star do something detectable before explosion? And it actually did. So what I'm showing here, and then what I'm showing in these stacked images to give you like a photometric or an actual picture visualization of what this is detections from the Young supernova experiment prior to a normal type 2 supernova. So prior to 20 TLF, we saw precursor flux, so precursor pre-supernova activity for approximately 130 days before the star actually exploded. So this is really, really amazing, and hadn't been seen before in a normal type 2 that evolved into this kind of 2 plateau. We've seen this in type 2Ns, and there have been some really amazing studies with ZTF and other things that have looked into precursor activities in type 2Ns. This is one of the more kind of unique events because it's coming from a type 2 supernova. So it's coming from just a normal red supergiant star that clearly had some enhanced mass loss because we saw that flash ionization spectrum. So we're kind of piecing the progenitor picture together with this really interesting detection of precursor activity, because the Young supernova experiment has the depth to push down at lower magnitudes and detect these types of emission for a nearby object. And 20 TLF was the first case where we actually were able to do that. So like I said, we're watching a red supergiant explode. So this is one of my favorite plots that I've made about this. So this is kind of a bolometric and then black body temperature and radius sequence of 20 TLF before explosion, at peak, and then all the way into its radioactive decay. So we're really if this plot shows you anything, it's that the Young supernova experiment is observing this precursor activity. The star explodes. It produces this luminous supernova light curve peak. It goes on to its plateau phase. It goes on to its radioactive decay tail. And what we've never seen really before in type 2s is this 120 days worth of actual activity leading up to what we usually see, which is this rise to peak, plateau, and then radioactive decay tail. So this is really, really amazing because we're able to constrain what the star was doing in a whole new way. In a way that was not indirect through flash spectroscopy, but rather direct. We're literally seeing a star do some crazy stuff right before it explodes, and then we have evidence that it ejected some mass and did all this kind of interesting pre-explosion behavior through the flash ionization lines that we saw in its spectra. So I'll touch really briefly on the nebular spectra. So I said that we just compared to nebular spectrum models for red supergiants, and we said that the star was likely low mass. So there's a typo there, but it's actually the likely zero age main sequence mass of 20 TLF was probably 10 to 12 solar masses. So now we have this low mass progenitor doing some precursor activity or pre-supernova mass loss that then is, puts CSM out into into the surrounding environment, shock breaks out, there's an ionization of this material, and then we see this photoionization spectrum with Keck. And we can go a little bit further and model the spectra and the light curves with radiative transfer models. And we can understand that there was really an enhanced mass loss rate of almost 0.01 solar masses a year. The CSM was really dense and confined to 10 to the 15 centimeters around the star. And we see that the actual red supergiant radius was pretty puffed up because it had to match the long plateau phase of this object. So we're estimating that the red supergiant was puffed up to around 1100 solar radii at the time of explosion. So that's pretty interesting because it links to a star undergoing some sort of precursor activity and then also puffing up, and we're really constraining some like phase space of red supergiant evolution prior to explosion that we just had no idea what's going on. I know I'm running a little low on time, but I really wanted to get into this final picture because I think I've thrown a lot of observational information at you, and I really just wanted to put it all together into one nice picture because I think as supernova scientists, like the ultimate goal is to put something tangible on paper and say, this is what happened with the star. This is what it was doing before explosion. This is the star that exploded, and look at the resulting supernova that we observed with all the amazing telescopes around the world. So to start off, before explosion, this was a red supergiant star, 10 to 12 solar masses at its zero age main sequence mass. It then shedded some material. It put this material into the outer CSM. It was puffed up a little bit to 1100 solar radii or so. What we saw then for about 100 days before explosion with the young supernova experiment observations is that this star was clearly undergoing some sort of process that drove off material from the stellar surface that then was emitting and illuminating and able to be detected by our telescopes for this 130 days in RIZ bands before explosion. And then what happened is that shock breaks out, the core collapses, shock breaks out from the stellar surface, it ionizes this material. That's where we get this photoionization spectra that we see, that we observed with Keck LRES, and we're able to constrain the properties of the CSM, the composition of the CSM, all together. We're looking at this red supergiant star that did this type of, had an episode or multiple episodes of enhanced mass loss right before explosion. And using a combination of observations, we're able to constrain this entire picture and put it all together. So that we're really, constraining a phase space of red supergiant and just massive star evolution that's just completely unknown. So I'll put up some conclusions. Like I said, 22LF is the first, normal or characteristic type 2 supernova with this confirmed precursor activity. Keck enabled flash spectroscopy, Keck enabled this late time follow-up, and all these modeling of this supernova allowed us to show that, enhanced mass loss was occurring. This star was puffed up right before explosion. And if we want explanations to try to explain why, precursor activity could be detected, it's most likely some sort of nuclear instability in the core of the star. This leads to the driving off of material once energy is injected into the outer envelope of the star. But this is a really complex, unknown process. So, the theorists out there, this is something that we're trying to work on to try to understand in better detail. All right, with that, thank you for having me. Thank you to the organizers, and thanks for accommodating me remotely.
Awesome, thank you. Okay, maybe one quick question, one or two. No, just one, yeah. Or yeah, just say it and I'll repeat it. Yeah.
Okay.
In the precursor activity, you flashed a black body temperature of 6,000 Kelvin. Does that seem a little bit hot?
Yeah, I mean, it is. It's hotter than a red supergiant would be radiating on its own. So this is clearly like probably the radiation coming from the material that is being driven off in this precursor outburst or activity. However, a black body temperature is only a lower limit on, where it actually is emitting, and a black body temperature is like imperfect. So how hot is that really? It's up for debate. A black body temperature is just kind of like a nice jumping off point for it, but it's definitely hotter than the stellar surface. So it's clearly like material that needed to be, driven off in some sort of outburst or ejection.
Okay, let's thank Wynn again